Hi guys, Mark here from Harwell XPS. Now, today we are going to be talking about Auger analysis, Auger electrons, and the kind of maths and process behind why these arise and what kind of information we can get from them. So, this is going to be a two-part video. Today, we are mostly going to be talking about the actual maths behind the processes, what dictates the kind of energies involved, and then in the next part, we're going to be looking in a bit more detail about some of the specific applications of the analysis of Auger peaks, what kind of information you can get from it, where it's useful, where it's kind of necessary in some cases, and we won't focus so much on the actual maths. So if you're not too interested in going into a deep dive on some of the equations, etc., then I will stick a link to the next video in this video now, so you can skip all of this and go and just kind of see how we might actually use these in practice and understand what kind of information you can get from this. So if you're staying here to watch the rest of this video, great. If not, I will see you in the next video. And for those of you that are staying, let's get into the main part of this video. Okay, thanks for sticking with us. If you are still here, we are now going to be looking at the Auger minor process and what kind of things affect the energies that we get from our eventual Auger minor electrons. So let's start by going back to basics. The photoelectron binding energies that we get when we record an XPS spectrum. Now, the process essentially is we are taking energy in the form of X-rays, which have an energy of HV. We are introducing those to an atom Z, and we are ending up with a core hole on our atom Z. So we now have Z plus and a free photoelectron. Now, the energy of the incoming radiation is equal to how much energy it took for us to remove that photoelectron from the atom, and then any left over is the kinetic energy that the photoelectron has as it's been removed from the atom. Now, this is the basic principle behind XPS. So the energy of this Z plus atom with the core hole above the ground state is what we refer to as the binding energy. And so this leads us right back to our photoelectric effect equation, where we have EB of Z plus. So the binding energy of Z plus is equal to HV, the incoming energy of the radiation, and then subtract from that the energy of the emitted photoelectron in kinetic energy terms. So quite often you will see referred to when discussing XPS Koopman's theorem, which states that the binding energy is equal to the energy of the emitting electron shell in the orbital. Now, this is a frozen orbital approximation. So what this means is this assumes that radiation comes in, an electron goes out, and nothing changes. That's basically it. However, we know that when we have an excited state like this, when we've removed an electron from a core orbital, this is not going to be the most energetically favorable configuration. So the atom is going to respond to the creation of this core hole in some way, and it does that by rearranging some of its electrons to fill that core hole and lower the overall energy. And the energy kind of penalties and processes involved in that rearrangement are called the relaxation energies, and this will ultimately affect the binding energies that we see in XPS. Because those photoelectrons, once they're emitted, the kinetic energies are going to be influenced by these rearrangement energies. So it is something that does influence XPS energies and plays a crucial role in understanding the Auger process and why we get the energies that we do. So a good approximation of this relaxation energy is around about 75 to 85% of the square root of the final ion energy. But if we want to look at this in more detail, it's helpful to first consider a completely isolated atom, and then reference to the vacuum level. The energies that we're looking at are going to involve two terms: a ground state energy which is symbolized here by epsilon, and then a relaxation energy. So this can be either atomic or intra-atomic processes at this point, which is symbolized by R. So now our equation becomes the binding energy relative to the vacuum level of the emitted photoelectron of an isolated atom is equal to the ground state energy minus the relaxation energy. Fairly straightforward stuff so far. But now if we take this into a more complicated system, so for example a molecule, a gas, we can now experience two additional effects which will influence the binding energies that we see. So the bonding to neighboring atoms can change the atomic energy levels by a factor that we're going to refer to as delta epsilon. So again, this is the kind of one of the fundamental concepts behind XPS, is that our initial state can change depending on the chemical environment of an atom. So this initial state change is reflective of the change in the energy levels as a process, as a result of the process of going from an isolated atom into a molecular system. The second effect is that electrons from neighboring atoms can also relax during this ionization process and reduce the total energy. So this introduces to us extra atomic relaxation energy processes. So think things like charge transfer processes. So now our equation becomes the binding energy of this photoelectron from the molecule relative to the vacuum level is equal to the initial state energy, the ground state energy of the isolated atom, plus a factor that we're calling the shift in initial state energy from going to an atom to a molecule. So this delta epsilon m minus the relaxation energy from the atomic or intra-atomic processes, which is generally not expected to change too much when going from an atom to a molecule, minus again the extra atomic relaxation energies, sometimes also called polarization energies, of going to from an atom to a molecule. So this extra atomic relaxation energy that we have involving electrons from neighboring atoms now means that we can think of a chemical shift between an atom and a molecule as a shift in the binding energy. So delta EB relative to the vacuum level for a photoelectron from going to an atom to a molecule is equal to this delta epsilon m minus the relaxation energy, the extra atomic relaxation energy of the molecule. So we're talking about a shift now, not an absolute energy. So we've removed the kind of more absolute terms, and we've now just got these relative terms that we can use as a kind of determinant between going from an isolated atom to a molecule. So finally, we're going to consider this shift from moving to from an isolated atom into the conductive state. The conductive state is very important later on when we come to actually performing some experiments and looking at these shifts relative to a conductive metal, because we can easily measure conductive metals. So knowing things relative to those is going to be important. So again, not expecting a significant shift in the atomic or intra-atomic relaxation energies, and the shift in the initial state energy is expected to be relatively small. But we've now got this equation where we have the shift in binding energy relative to the vacuum for the photoelectron when going from an isolated atom to a conductive solid is equal to this delta epsilon c, so the change in the initial state energy for when going to a conductive state, minus the relaxation energy, the extra atomic relaxation energy going into this conductive state, which is again is expected to be the dominant factor in determining these shifts. Okay, so finally on binding energies, when we go into a conductor, we expect that this extra atomic relaxation energy for the conductive state is going to be related to the ionic charge and the minimum electron screening distance and the dielectric constant by the equation RCEA equals the square of the ionic charge divided by twice the minimum electron screening distance times 1 minus 1 over the dielectric constant. So what you can see here, hopefully quite easily, is that these relaxation energies are going to be influenced by characteristics of the atom, particularly ionic radius. So smaller ions are going to impart bigger relaxation effects and have bigger changes on the resultant energies involved. Okay, so now that we've covered binding energies, we're going to be moving on to the kinetic energies of the Auger electrons. So essentially we can think of the kinetic energy of the Augers as the difference between the initial and final state. So we create our core hole, we emit our photoelectron, we have an electron in a lower binding energy state, so a higher overall energy state, which will relax, fill that core hole, and then excite another electron. And so the energy that it loses from going from the higher energy state to the lower energy state is essentially going to be the HV in our photoelectric effect relationship. So this gets transferred entirely to the emitting Auger electron, and this is released as kinetic energy. So the mathematical representation of this can be thought of as kinetic energy. So E, again, all relative to the vacuum level of the Auger from an isolated atom A, is equal to the binding energy of this K plus state. So we're looking at a KLL Auger here. So the binding energy relative to the vacuum of this K plus, as we were talking earlier about Z plus, minus 2 times the binding energy relative to the vacuum of L plus. So these are the electrons involved in the Auger process, plus a static relaxation term minus so an electron-electron interaction term. So because we've got a double vacancy in the final state, we just need this interaction term for completion. Okay, so just a quick note on what the static relaxation energy term in the previous slide is referring to. So we want to break this down into some of the contributing factors. So we have the total two-hole relaxation energy, the relaxation energy of the system in response to the creation of these two core holes due to the Auger process occurring in this as a result of the original photoemission process. Now we can also think of the one-hole system and what the dynamic relaxation energy for the one-hole system might be. Now, because in that system we have a completely isolated hole, it's not subject to any additional effects from a second hole, unlike the two-hole system. So our static relaxation energy can be thought of as the difference between the total energy of a kind of two-hole system and 2 times the energy of the individual one-hole dynamic system. So this kind of refers to the additional response of a double vacancy as opposed to 2 individual vacancies. Now this is only going to be particularly important for later on when we come to talk about our Auger parameter shifts and how this relates to some of the initial and final state contributions. But the total two-hole relaxation energy, the equation for determining this is 4 times the one-hole dynamic relaxation energy, which means if we plug that back into our expression for the static relaxation energy, where we have this Rs equals RT minus 2RD, what we will now end up with is Rs equals 4RD minus 2RD, which we can of course simplify down to Rs equals 2RD, and that will crop up again later when we talk about how we extract some more quantitative information from our Auger parameter shifts and how we can get some more of the individual energetics out from an Auger parameter shift. You should remember earlier we had this relationship for binding energy where we deconstructed this into the initial state energy and the relaxation energy. So we have the binding energy is equal to the initial state energy minus the relaxation energy. So what we're going to do is put those terms into the relationship that we had 2 slides ago. So if we just quickly go back, where we have this kinetic energy of the Auger equal to the binding energy for the K shell minus 2 times the binding energy for the L shell, plus this static relaxation term and the double electron interaction term. So we're going to put the deconvoluted initial and relaxation energies into that relationship, and what we end up with now is the kinetic energy of the Auger for the isolated atom is equal to the ground state energy of the K shell minus the relaxation energy of the K shell minus 2 times the ground state energy of the L shell minus 2 times the relaxation energy of the L shell plus this static relaxation energy minus the double electron interaction term. So as we did before for the binding energy, we're now going to look at the shift from the isolated atom to the molecule. Again, we're just talking about gas phase molecule, and what we end up with is this delta EV. So the delta, the shift in the kinetic energy relative to the vacuum level, going from an isolated atom to a molecule for an Auger minor electron is equal to the shift in the initial state, the ground state for the K shell for the molecule, minus 2 times the shift in this initial or ground state energy for the L shell, plus the extra atomic relaxation energy term for the LL shell, minus the extra atomic relaxation energy term for the molecule for the K shell. Now, the actual chemical shifts for different shells, so for example for the K shell, for the L shell, experimentally these are very close. So we can actually simplify this, remove the 2 terms for the different terms for K and L, and what that leaves us with is a new relationship, which is the shift in the kinetic energy for the Auger electron going from the isolated atom to the molecule is equal to the negative shift in the initial state energy for the L shell or the K shell, doesn't matter, plus the extra atomic relaxation energy of the molecule for this double core hole, minus the extra atomic relaxation energy for the initial core hole. So again, we're going to conductive solids, and again our chemical shifts in for our initial state, our ground state, are going to be pretty minimal. So we are going to be dominated by the relaxation energy terms. Now, if we remember back to our relationship for the extra atomic relaxation energy in a conductive solid, you will recall that one of the terms involved was the charge on the ion. So we have E squared as one of our terms. Now, we have 3 terms in our relationship from the previous page. We have the extra atomic relaxation energy for the K shell and 2 relaxation energy terms for the L shell. Now, in the K shell system, we have a single point charge. In the doubly ionized system, we obviously have an ion charge of 2. So we're going to have a difference of 4 essentially in this once we've squared that. So if we add up our K, our L and our L, we have 3 individual relaxation energy terms. So if we have if we are using our L shell as our model that we're using for the calculations, we would have relative to the K shell 1/4, because the point charge is that much lower. So if we were to add these together, so you have 3 and a relative ratio of 1/4 for the K versus the L, we now end up with a system where we have the shift in the kinetic energy of the LJ going from an atom to a conductive solid is equal to the negative initial state energy of the conductive solid of the L shell plus either 3/4 of the extra atomic relaxation energy for the L shell or 3 of the extra atomic relaxation energies for the K shell in the conductive solid. Okay, so we are on the home straight now. And so finally we're going to be talking about the actual Auger parameter itself. Now this is defined as the difference between a photoelectron core line and an Auger peak. A lot of you may be familiar with this already. Very useful term because it's free from any complications due to sample charging, work functions, etc. It's just a difference, so they all cancel out. And this can be determined using the relationship here, which is the Auger parameter, symbolized as alpha, is equal to the kinetic energy of the Auger minus the kinetic energy of the related photoelectron peak. Now, the eagle-eyed among you will probably have spotted the problem with this already. If you use different photon energies, you're going to be changing the difference between these two peaks, because the Auger peak will always appear at a fixed kinetic energy, but if you increase the energy of your photon source, you'll increase the kinetic energy of your photoelectron peaks. So you can't really compare this reliably between different photon energies. So to compensate for this, a new term was adopted, which is the modified Auger parameter. This is what everybody means now when they use the term Auger parameter, and this uses the photoelectron core line's binding energy instead of kinetic energy, and you're left with this relationship here, which is that the modified Auger parameter is equal to the kinetic energy of the core of the Auger emission plus the binding energy of the core line, or written another way in the context of the original Auger parameter, this is the kinetic energy of the Auger minus the kinetic energy of the core line plus the photon energy. So you can obviously do this conversion, but it is easier to deal with the modified Auger parameter, a binding energy and a kinetic energy of the Auger peak itself. And now, of course, these shifts will be identical regardless of whether we're using the Auger or the modified Auger parameter. We're going to stick with the original term as we move forward, but as I say, these shifts are identical whether you're talking about delta Auger parameter or delta modified Auger parameter. So based on our previously discussed relationships, binding energy of this ionized atom Z is equal to the photon energy minus the kinetic energy of the emitted electron. The binding energy of the photoelectron is equal to the initial state energy minus the relaxation energy, and then the relationships that we've just discussed about the kinetic energies of the Augers, we can now combine these all into a single expression for the Auger parameter, where we have the Auger parameter of an isolated atom is equal to 2 times the initial state energy for the K shell minus 2 times the initial state energy for the L shell minus 2 times the relaxation energy for the for the ionized K shell plus 2 times the relaxation energy for the ionized L shell minus the photon energy, because remember we converted our Auger parameter back into kinetic energy by incorporating the photon energy again, minus the double electron interaction term plus the static relaxation energy for the double core state. So in a similar manner to what we've been doing already, if we look at the shift in the Auger parameter when going from an isolated atom to a molecule, we're left with the extra atomic relaxation energy for the LL double core hole state minus 2 times the extra atomic relaxation energy for the ionized K state, and then going from an atom to a conductive solid, we have this extra atomic relaxation energy for the double core hole state in the L shell for the conductive material, minus 2 times the relaxation energy for the ionized case shell for the conductive material. And going back on our previous assumptions, where the extra atomic relaxation energy for this L plus for the molecule is equal to 4 times the extra atomic relaxation energy for the ionized K state. If we recall our E squared term, the charge on the ion term for our extra atomic relaxation energy relationship, then when we look at the shift in our Auger parameter going from atom to conductive solid, what we're left with is the extra atomic, so half the extra atomic relaxation energy for a conductive material for the L plus state is equal to 2 times the extra atomic relaxation energy for the ionized K shell for a conductive solid. We're nearly there. Okay, so finally, we're going to be looking at going from a conductive solid to insulating materials of probably the vast majority of things you might want to study by XPS. Probably not going to be perfect metals. You're going to be looking at insulators and semiconductors, and you'll want to know how to apply these to your eventual materials. So the shift in the Auger parameter from going from a conductive solid to an insulating material can therefore be derived from half of the extra atomic relaxation energy going to an insulated material for the L plus minus the extra atomic relaxation energy for the conductive material for the L plus, which is also equal to 2 times the extra atomic relaxation energy for the ionized K state, because again we have this relationship from the charge on the ion. So we now actually have a shift that we can measure. We can get reference data on conductive solids in the forms of metals and then compare those to our unknown materials. And we have these relationships now that we can start to maybe extract a little bit more information from. If you look at how these delta Auger parameter values scale for a range of materials, you will start to see that this shifts strongly with the polarizability of the atom. We will talk a bit more about this in the following video. But essentially, the more polarizable a species is, the closer this delta A will be to 0 in the conductive solid state. So straight away you can see that this can be quite a useful way of probing the kind of covalency, the polarizability of a system. Okay, thank you for sticking through all of this. If you have, appreciate there's a lot of terms. You may be able to hear that my voice throughout this video has started to struggle a bit, so I'm going to go and get a coffee, and then we will return in the next video to actually talk about how we can use this, what can we use it for, and what kinds of information can I get out about my samples that I maybe can't get out through other methods. So thanks again for watching, and I hope you found it useful, and we'll see you soon in the next video. Cheers.